Good morning again. Today we will be going on to something that is quite relevant to computer science. So today we will be looking at projection again. We did that when we did Gram-Schmidt, but at that time we were thinking of projecting to a single vector, one vector being projected onto another vector. Actually, we did look at projecting on subspaces, but we didn't explicitly say it. So today we'll be doing it. And what we will end up with will be an operator, a matrix that will do the projection, and we'll look at the properties of that matrix. And much more importantly and more to the point in this course, we will be developing the algorithm, linear regression algorithm, from the concept of projection. That is something that I find very satisfying to teach, and I hope you will find it satisfying to learn also. So let's do a recap. We did it in Gram-Schmidt, as I said, where we used the angle between the vectors. So given any two vectors, red one and blue one, A and B, if we were to find the projection of the blue one along the direction of A, and we'll call it a light blue one, B hat, and that is the idea. That is what we did in Gram-Schmidt in order to get the second column. Before doing that, we have to ask ourselves, why are we spending time learning how to project? What's the idea? What does it give you? So one way of thinking about it is that a vector A is a vector, of course, but it also defines a subspace because that is a direction. All scale versions of A will be along that direction, along that line. So projecting onto a vector A is also projecting onto that subspace. So if I have a vector and I'm projecting onto the subspace, what the projection gives me is a vector in the subspace that is closest to the one that I'm projecting. Suppose I have a red vector A, and that defines a subspace that's along that line. I have a blue vector B. When I project onto A, I get some vector here, and my claim is that that is the vector in that subspace that is closest to B. So this is my B, and this B hat is the one that is closest to B. How do I define closeness? So if I look at the tip of this vector and tip of the projection, and that distance is the smallest. If I take any other vector on A, say this guy as a projection, let me call that B hat. If I did, then that distance will be more because the closest would actually be the one that is along the perpendicular direction of A. So that is something to keep in mind. You will see why that is important. So the projected vector is along A, and if for some reason we had access only to the subspace, not to the whole space as we saw here, we have R2, but suppose we had access only to that red line for some reason, for some mathematical reason, then the best we can do, the best approximation of B that we can have is B hat. That might sound a bit wishy-washy at this point, but stay with me. But let's review how we did it before we move on. So while doing Gram-Schmidt, we did it this way. We had two vectors, A and B, with an angle theta between them. And we know the dot product in terms of the cosine of the angle between them. So that is the norm of A times the norm of B times the cosine of the angle. And then we know what the cosine of the angle is. So take the dot product and divide by the norms. And if we want to know the projection, all we need to know is the length, as I show you here, the length x. And then you multiply by the direction A, and then you'll get the projection vector. So x is easy to compute using basic trigonometry. X is the adjacent side, so it's the hypotenuse times the cosine of the angle, and we know the cosine of the angle, so we'll get that. Cosine of the angle is that, and multiply by the norm of B, then the norm of B from the denominator goes away, and you get that. But we actually want the projection vector, which is a vector along the direction A with the length x. The direction of A is a unit vector along A, that will be A divided by the norm of A, and times x will give you the B hat, the vector that you're looking for, the projection vector. And that turns out to be A transpose divided by A transpose A, because I have the norm of A appearing twice in the denominator, that is norm of A squared. But keep in mind that this, when we talked about norms, we talked about P norm, and this is actually true only of Euclidean norm. A transpose A will have some product of the elements of A with itself. The first element times the first element, that is the first element square. So the square comes in. Okay. So this definition or this statement is true of Euclidean norm, and that appears with a square. Keep that in mind. So that is what I have. A, norm of A times norm of A squared, so A transpose A. And in the numerator, I already have A transpose B, and then I multiply with A coming from the direction of A, so that is A transpose. That gives me a nice little form, A transpose divided by A transpose A, and that is like an operator operating on any vector B. That will give me the projection of that vector along, so we can define this as the projection operator, and that is a matrix. But that method was not the linear algebra way of doing it. So we'll look at it again using linear algebra, and you will see that it's a lot less messy. So the way to think about it is this: given any two vectors A and B, the projection of B along A is B hat, and there are many vectors along A, an infinite number of vectors. We have to choose the right one. How do you choose the right one? So in order to choose the right one, we define the perpendicular distance that we saw here, the perpendicular distance here, and choose the one with the lowest perpendicular distance. That's what we want to do. And the lowest will happen when that perpendicular vector is perpendicular to A. So that's what we want to do. So the projection of B is in the same direction as A. So it's a scale version of A. So let's call that scaling factor X. So the error now is what? It would be minus B hat, and that is the error. Okay, so we'll call that the error vector, and that is B minus B hat. That will give me B hat is equal to B minus the error vector. That is XA, some scale version of A, because B hat is along the direction of A. For my own purposes, instead of writing it XA, I'm going to write it AX, which I'm allowed to do because scalar multiplication is commutative. So let me show this to you using better graphics. I have A there, that is a line that defines the subspace of A, and then I have a vector B there, and I have B hat, and among all the vectors along A in the subspace of A, I'm choosing this particular one because that perpendicular vector is the smallest possible one. So that is the vector. Since all our vectors start from the origin, I move it to the origin. Then I can say that B is actually B hat plus the error. So B hat, I move E to the tip of B hat and I'll reach B. So B is B hat plus E, which means B hat is B minus E, and that has to be along the direction of A, which means there's some scaling factor X which will say that B hat or B minus E is equal to AX. So that's all I want to say. By construction, the error vector E is orthogonal to A. It has to be. That will be the vector that is closest to B along the direction of A. That will happen only when E is orthogonal to A. If E is not orthogonal, if E is in some other direction, then that length is obviously not the smallest. This one would be the smallest because that is the orthogonal one. So it is orthogonal to A. What does that mean? That means A transpose E has to be 0. Now error added to the projection vector B hat is B because that is the error. So B is equal to B hat plus the error vector E. So E is B minus B hat. So E is B minus B hat. That means A transpose times B minus B hat, that is the error, that is equal to 0. So since the projection B hat is along the direction of A, we call it A times X hat. X hat being the right scaling factor, so that I get B hat. So I can write B hat is equal to AX hat, or A transpose B minus AX hat is equal to 0. I know that this becomes kind of sounds like I'm going around in circles. I'm just guiding you through a series of steps that will take me to the right answer very soon. So what I'm saying is A transpose times an error vector is equal to 0. A transpose dotted with an error vector equal to 0 because A transpose is orthogonal to the error vector, and the error vector is the original vector that I want to project minus the projection. So that is the definition of the error, and the projection has to be along the direction of A. So it's a scale version of A, and the scaling factor is X hat, and if I can find X hat, then I'm done. But I have an equation right here that will give me X hat. So if you look at this guy here, you can actually see something similar, remnants of our favorite equation AX equal to B. It is already there. Everything somehow comes back to AX equal to B in our course. So let's look at it again. So I have A transpose, that is a dot product of A with the error vector, B minus the projection, which is AX hat, is equal to 0. So if I just expand it and move this guy to the to the right hand side, I get A transpose B is equal to A transpose A x hat. A transpose B is x hat A transpose A. Okay, so I can get x hat right there. So x hat is just a number, and A transpose A is a dot product, is actually the square of the norm of A. So that is just a number also. So x hat is A transpose B, which is a dot product, divided by that guy. Now, the projection I want is not just the number x hat. I actually want the vector b hat, meaning I want to take x hat and multiply that by a. So b hat is actually a times x hat. So b is equal to x hat, which is here, that is the same as this, times a, and then I can move it around. This guy is actually just a number, so I can move that to the other side of a, and then I can move this to the numerator. I get a transpose divided by a transpose a times b. Again, I get this operator. That is a matrix. A transpose is an n by n matrix, and that is the operator that will take me from a vector to its projection onto the direction of A. So now, how could I write these things? Because I have associative property of matrix multiplication, I can group them in any way I want, can do any multiplication first. A transpose B is the same as A times A transpose B, and I can basically group them in any way I want. Any grouping is valid. And if there is a scalar multiplication, I can always move that scalar around. So all those things are fine. So we came up with the projection as A transpose divided by A transpose A. So A transpose A below is just a number. So ignore that for a minute and then look at the shape of A transpose. That's a matrix because A is n rows and one column. That's a vector. A transpose then is one row and n columns. A transpose is an n by n matrix. The projection matrix, if you define that as A transpose divided by A transpose A, then I get a matrix, n by n matrix, but what's its rank? Its rank is 1. So let's take an example. A is a column vector 1, 2, 3. So A transpose is 1, 2, 3 in a row. It's a row matrix. And if I do the multiplication by the row picture, the rows of the product are linear combinations of the rows of my matrix on the right scaled by the weights in my matrix on the left. So the first row is a 1, 2, 3. So 1 times 1, 1 times 2, 1 times 3. The second row is 2 times 1, 2 times 2, 2 times 3. So 2, 4, 6. The third one is 3, 6, 9. So you can see that the matrix, the second row is just twice the first row. The third row is 3 times the first row. They are all basically linear combinations of scaled versions of one row. It has to be because we have only one row. So there is only one linearly independent row. And if I actually do Gaussian elimination on this one, I'll take twice the first row, subtract from the second one to get all zeros. 3 times the first row, subtract from the third row to get all zeros. So 2 0 rows, only one row with pivot. So rank is 1. Also, A transpose, if I transpose the whole thing, I get A transpose. It's symmetric. You can actually see it here. So 2 and 2 here, 3 and 3 here, 6 and 6. So it's symmetric. It has to be. So some properties of the projection matrix, symmetric and rank 1. So that is my projection matrix again. So given any vector B, a blue vector, the projection is already along A. But if I do it twice, if I project the projection, what will happen? The projection is already along A. If I project it again, since it's already along A, it's not going to change. What that means is that if I take the square of the projection operator, or rather, if I apply the projection operator twice on a vector, it is the same as applying it once. So that you can see by just multiplying P by P. So A transpose, A transpose, A transpose, A transpose, A transpose, A. If I do that, and then if I do some kind of grouping, I can see that the purple part will just cancel off, and I'll get P square is equal to P. It doesn't matter how many times you apply it, you always get the same answer. Multiple applications don't actually change the answer. And I think the name for such matrices is actually idempotent. P square is equal to P implies that P is idempotent. So if I look at it, does it imply that, can you cancel P on both sides and say P is equal to I? P square is equal to P. Then can I write P square times P inverse is equal to P times P inverse, right multiplying by P inverse, and this would imply P is equal to I. Obviously I shouldn't be able to do this, and can you see the reason why I should not be able to do this? P has no inverse, and that is true. P inverse does not exist. It is not invertible. Why is it that it's not invertible. Now P is a square matrix, A transpose. So this is in R n by n. So it is a square matrix. It is not full rank. P is a rank 1, so it is not a full rank matrix. But can you see a situation where P inverse does exist? Rank 1 is not full rank as long as n is greater than 1. But if n is equal to 1, if you're working with a one-dimensional space, just real numbers, then P inverse does exist because P is just a scalar and P inverse is just a reciprocal. Linear algebra is actually wonderfully consistent. Whatever kind of little inconsistency you try to find, you will always fail. I was trying to find an inconsistency saying that in one dimension maybe it fails, it doesn't. So the reason is basically that it is rank 1. But the reason why it is rank 1 is that it actually destroys information. When you project a vector onto another vector, you're actually throwing away some part of the information. What will happen if I take a vector, project it, and if I double the vector? If you double the vector B, obviously the projection will double. What happens if you double the vector A? The projection should not change because A, the purpose of having a vector A is just to define the line, define the subspace, define a direction. That means regardless of what the length of A is, the projection will not change. That means the projection operator cannot change. So let's verify that. So suppose I double A, what happens is that wherever I see A in P, I'll just put 2A and we'll just have a factor 2 times 2 in the numerator and 2 times 2 in the denominator. That will give me just P. That will just cancel off. And the inversion of P cannot be done because we lost information in making the projection, which means multiple vectors B can actually give you the same projection B hat. And we saw that it is actually a rank 1 matrix. And the last thing I want to ask you is P a linear operation? Multiplying B with P, it will give me the projection, but is it linear? Yes, it is. A multiplication by a matrix is always a linear operation. That is the definition of linearity because we started, remember, that's why I asked you to go back and look at the early chapters once in a while. Because we came up with the concept of a vector and a matrix because we started with the notion of linearity. So it is a linear operation. Now the question is, how do you distinguish between P the permutation matrix and P the projection matrix? Well, basically that is a chiding on using the same symbol for both these things. But since both these words, permutation and projection, begin with the letter P, it's not my fault. It is a fault of English language. And you will distinguish it, will differentiate between those two using the context. So actually, in order to make sure that P is a linear operation, you can actually do the tests of linearity if you want to. You can scale and sum, etc. And homogeneity, additivity, those conditions. Multiple vectors can give you the same projection. If I have a B, projection is like shining light onto the tip of B in a direction that is perpendicular to A. So I get that as my B hat. But any other vector whose tip is on that perpendicular line will give me the same B hat. Okay, several vectors will have the same projection B hat, which means given a B hat, I cannot really tell which B it came from. I cannot reverse the operation. So P is a singular matrix by its very nature because multiple input vectors will give you the same projection. What's the column space of the projection matrix P? Taking a projection of a matrix of a vector P is multiplying that vector on the left by P, which means you're taking the linear combination of the columns of P. So this multiplication here, we're taking the linear combinations of the columns of P. So the projection, which is P times B, will be in the column space of P. So the product has to be in the column space of P. But all products, regardless of what B is, will be in the direction of A. Remember, that is what projection is. Projection operation is an operation that will take a B to the direction of A. So the column space of P is actually just a line that is defined by A because the projection has to be along the direction of A. That is obvious because that is the definition of projection. But this multiplication basically says that the product has to be in the column space of P. That means the column space is actually just a line that is defined by A. So that is an interesting property. And the dimension of the column space is the rank of P. And we saw that P is a rank 1 matrix. So there is only one line that is in the column space of P. Column space of P, if you were to write it, but you can see it by looking at the matrix. I started with an A as an example. 1, 2, 3, remember? 1, 2, 3. And I had A transpose, which was 1, 2, 3. then AA transpose, which is the numerator of P, this divided by some S. So ignore the S for now. So this is like 1, 2, 3, 2, 4, 6, 3, 6, 9. So this is a matrix that we got. And we see that this is actually symmetric. And the first column here, this column here, is actually just A. And all of the columns are this is 2A and this is 3A. And the column space is actually just linear combinations of the columns, which means scalar multiples of A. So just one line. The column space of P is a scalar multiples of A. So the rank of P is 1, is a rank 1 matrix. So if you were to store a rank 1 matrix, if you want to store an n by n matrix, a general n by n matrix, a full rank matrix, you need n square storing locations. So if it is a 100 by 100 matrix, you need 10,000 floating point locations in the memory. But if you know that that A is actually rank 1, then all you need would be 100 numbers to store one row and then 100 more numbers to store the scaling factors for all of the rows. So it is like 200 floating point locations rather than 10,000. And similarly, if you were to do any kind of operations on this matrix, there will be corresponding kinds of savings if you were to write those programs carefully. If you know that something is a rank 1, you should be able to use that in programming. So we know how to project to a vector now. So the projection operator there is A transpose divided by A transpose A, and that's it. That's the projection operator. Multiply any vector with this projection operator, that will project the vector that you're multiplying to A. Now let's talk about a subspace. Actually, if you think about it, projecting onto another vector A is the same as projecting onto the subspace defined by that vector A. So we saw that it's the same as projecting to the line defined by that vector A. And A would be the basis for that line. For that one-dimensional subspace, you need only one vector to specify it. That would be A. So that's what I've written down there. Projecting to a vector A is the same as projecting to a subspace S defined by A, which will be a subset of Rn, given that A is a member of Rn. So basis for that subspace would be just A. Now, suppose the subspace is not just a one-dimensional subspace, but an R-dimensional subspace. Say R is 2. So how do you specify a subspace? So all you have to do is to specify the basis vectors. So in the case of R, you have to specify R basis vectors. That would define the subspace in Rn. And then we're hoping that we will be able to project onto that space. So of course, when you're specifying the subspace using basis vectors, the vectors will have to be linearly independent. That is a requirement of a vector to be a basis vector. But they don't have to be perpendicular or normalized. Now again, before actually going there, let's figure out why is it that we are actually trying to project to a subspace. So this is where the interesting part of the game starts. So if you have a set of linear equations Ax equal to b, and with the number of columns much less than the number of rows, meaning it's a tall matrix, many more rows than columns, and that happens to be a typical case where you have a lot of data. Data would be a measurement of a bunch of features, as you will call them later, a bunch of features, but many measurements. So many more observations than the features typically. So if it is a facial recognition kind of data, typically you might have, I don't know, a 24 by 24 matrix or something. That would be 24 times 24 times maybe 3 or 4 as a number of different colors that you're using. And those would be the features. You will have 1,000 or 10,000 or 100,000 different phases coming in, different measurements coming in. Those are all observations along these finite number of columns. Now, if you think of this data matrix as a coefficient matrix of some equation, some set of linear equations, Ax equal to b, A is a data matrix. Why you want to look at it that way will become clearer later, but it's a matrix. The moment you have a matrix, you can think of that as a part of a system of linear equations. Then that system typically cannot be solved because you have more equations than variables, more rows than columns, and there is no guarantee that all the observations are going to be consistent. In fact, it's almost guaranteed that they will not be because of measurement errors and statistical fluctuations. It is almost always the case that all the columns are going to be linearly independent. It's going to be a full column rank matrix because of noise and independence of measurements and statistical fluctuations and all those things. So if you do the Gauss-Jordan elimination on A, you will get m minus n rows. Remember, m is a number of rows much greater than the number of columns. They will all be zeros, and all of them will turn out to be non-zero on the constant side if you take one of the columns as the constants. So that is always the most likely scenario. So B is not going to be in the column space of A, which means you won't be able to solve it. So given such a situation, assuming that you want to solve this system, how will you do it? Now, you might think that, okay, you have m equations, m is much larger than n. Just take only the first n of them and throw away the rest. That is not a good idea, because even though the equations are not consistent, you don't know which one is correct, or in general, none of them is really correct per se. All of them will have information content. So you don't want to throw away information. You want to use all of them, but you won't be able to solve. And in that case, since these equations do contain information and B is not a member of a column space, if we can project onto the column space, if we can find B hat which is in the column space, that will be the vector that is closest to your constants vector in the column space. And that equation you will be able to solve. So if you say the best possible solution or the best approximation to the solution is x hat, and that will be ax hat equal to b hat, where b hat is guaranteed to be in the column space because you're projecting onto the column space. So this is the basic idea behind why you want to project it. I know that even now the motivation is not completely clear, but because of the very nature of the flow of this particular lecture, the motivation can be clear only after you actually finish the lecture. So stay with me. So let me actually show you what's going to happen when you're projecting onto a subspace of 2 dimensions in a 3-dimensional space. So you have R3 here, x, y, z, and you have a subspace which is a plane going through the origin. So the subspace, being a subspace, will have to contain the origin, and that is S. How do you specify S? You take any 2 linearly independent vectors in the subspace S, A1 and A2, not necessarily normalized nor orthogonal or anything, just 2 vectors that are not combinations of each other, meaning one is not the scalar multiple of the other one. The moment you have that, and suppose you have another vector B, this B is not in the red subspace, it's actually sticking out. Assume that it's coming towards you compared to the red subspace, so it's not on that plane. So you want to find the vector that is closest to B in the red subspace S. So what you will do is you will project B to A1, the first basis vector, and also to A2, so that will be B1 hat and B2 hat, and then suppose you add them up, and now you look at the vector that is B hat defined by the addition of these 2 projections. If you look at that vector, that is like the shadow of B on the plane S. And in particular, if you take the error vector, which is from the tip of B hat to the tip of B, E is going to be perpendicular to A1 and A2 because you constructed it that way. You projected B to B1 hat and B2 hat, and then you added them up. So whatever is left will be perpendicular to the plane S. In fact, this is exactly what we did in Gram-Schmidt when you wanted to go to the 3rd column, when you wanted to normalize, you wanted to find the orthonormal 3rd column in the matrix Q. This is exactly what you did. You projected the existing vector onto the existing 2 normalized Q1 and Q2, and then you subtracted it away to get the error vector, and that we said that was perpendicular to A1 and A2, or Q1 and Q2 in that case. E is actually perpendicular to A1 and A2. So if you move E to the origin, that would be the vector, because all vectors start from the origin. So that will be the vector that is orthogonal to the plane S, which means it's orthogonal to the basis vector. So this is the projection that we want to do. So let's take the subspace as a plane in R3 as we did. S is a subset of R3. Dimension of S is 2 as we saw, and the basis is A1 and A2. Okay, A1 and A2 cannot be on the same line because basis vectors cannot be linearly dependent on each other. So A1 is not a scalar multiple of A2, that is guaranteed because they are basis vectors. Now the vector B, the projection B hat, will be such that if B is already in the subspace, then B hat is the same as B, because the projection, you take the shadow of B by shining light on it perpendicular to S, the shadow is going to be the vector itself because it's already on the plane. So B hat is going to be on S if B is already on S. If not, B hat is going to be on S because that is the projection, and B hat is going to be some linear combination of the bases, and let's call the linear combination with x1 hat and x2 hat. Those are the scalar multiples that we need to multiply the basis vectors a1 and a2 such that you get b hat. So let's start from there. Now b1 and b2 hats will be projections of b along the basis vectors a1 and a2 as we saw. Now if you take the error vector b minus b hat, that is the green error vector, and what we are insisting is that that should be perpendicular to the subspace, which means it has to be perpendicular to each one of the basis vectors. If something is perpendicular or orthogonal, I should say, to a subspace, it is orthogonal to each one of the basis vectors. Think of the subspace as the xy plane, and the only orthogonal vector that you can find to the xy plane is along the z-axis, or orthogonal vectors that you can find are along the z-axis, and that is perpendicular to the basis vectors x direction and y direction. So that is the nature of orthogonality. So again, B is A1 and A2, some linear combinations with x1 hat and x2 hat as the scalars. And if you were to write that as a matrix equation, and if you put A1 and A2 as the columns of a matrix A, and x1 hat and x2 hat as a vector x, then you get our favorite equation, B hat is equal to AX hat. So A is a matrix, the basis columns AI, A1 and A2 in this case, and B hat is the projection, which is a linear combination of the columns of A, because it's a linear combination of the basis vectors A1 and A2, and we just put those basis vectors in a matrix. So what that means is that B hat is one of the linear combinations of the columns of A. That means B hat will have to be in the column space of A. So the projection vector is guaranteed to be in the column space of A. So let's take stock of whatever we did so far. The problem that we're faced with, we have a full column rank tall matrix A. In this example that we did, we had 3 rows and 2 columns, so the rank was only 2, but that's the maximum rank you can have, so it's full rank, full column rank. So for a general B that you take, Ax equal to B will not have a solution because B is not guaranteed to be in the column space. So our strategy is to project B to the column space of A as a B hat. Then we get B hat is equal to Ax hat, or Ax hat is equal to B hat, and that is guaranteed to have solutions because B hat is guaranteed to be in the column space. But the price that we pay here is that we are not actually solving for x. X doesn't exist, there's no solution really, but we are solving for x hat, the best possible solution, the best approximation to the solution. So that is the best we can do. So there is an error involved here, and the error is quantified or represented by the error vector E, which will be the original constants vector minus the projection onto the column space. So now let's think about it slightly differently. We know that the error vector is orthogonal to the subspace that you're projecting to. That is why the projection is the closest one in the subspace. So error is actually orthogonal to the column space. What is the orthogonal complement of column space? The orthogonal complement of column space is the left null space. That we will come to in a second. Whatever I said is fine. We still need more information about how to get B hat such that we can solve Ax hat is equal to B hat. So you need to have some more information about the error perhaps. First thing to note is that E is orthogonal to the column space, which means E is in the orthogonal complement of the column space. What is orthogonal complement? Orthogonal complement is the set of all possible vectors orthogonal to a subspace that you're talking about. And what is the orthogonal complement of the column space? That is the left null space. So here is where the left null space, that is coming to it on its own, and then the error is a member of the left null space. Now, how do you solve the bunch of linear equations, the system of linear equations, when it is actually not solvable? We say that the error vector is orthogonal to the subspace, the red plane. What that means is that the error vector is orthogonal to each one of the basis vectors is orthogonal to AI. That means A transpose E is equal to 0. That is the definition of orthogonality. Error vector is orthogonal to each one of the basis vectors. So you have the vectors transposed as rows, and then you have the error vector, and that says something like A transpose and error vector multiplied will give you the 0 vector. What does that mean? Ax equal to the 0 vector, A is equal to the 0 vector. That will mean that X is in the null space of A if you have A transpose Y is 0. By the same analogy, or just looking at the symbols there, you can say that the Y vector now is a member of the null space of A transpose, and that null space is the left null space. So that basically means that the error is actually in the left null space, which we saw because it is orthogonal to the column space by definition, and anything that is orthogonal to the column space is in the orthogonal complement of the column space, and the orthogonal complement of the column space is the left null space. Error vector is in left null space. Since E is in the left null space, E is the same, and also because E is the same as that, E is a B minus B hat, which is B minus A times X hat. So this is the error, and A transpose times E is equal to 0 as you have here. So A transpose times B minus A X hat is equal to 0. So all these things might look a little complex to you, but this is what it is. It is just substituting for E in this equation from the definition of E. E is the difference vector between the projection and original vector that you're projecting. And what it gives you is something quite interesting. It's A transpose B minus A transpose A X hat is equal to 0. Rewrite it, taking one to the other side. What we were trying to solve was AX equal to B, which we could not solve. Now it looks like you just multiply with A transpose on either side, then suddenly this is actually solvable. But of course you don't get the solution because it's no solution, but you get the best possible solution. So this is the recipe for actually solving. So if you have a matrix A, part of a data matrix, and you have some B constants vector, you know that there is no solution, AX equal to B doesn't have a solution. All you have to do is to multiply both sides on the left with A transpose, then suddenly magically it becomes solvable. Okay, that is not solvable. Multiply the coefficient matrix on the left with A transpose and the constants vector on the right hand side also, then suddenly it is solvable. So this is what you have to remember. So if you stare at it a little bit, you can see that this is actually what we call the gram matrix, and in our case we had many more rows than columns, and the rank was n. So A transpose A is n by n matrix and its rank is n. We proved at some point that A transpose A transpose will all have rank, the same rank, and in this case A has the rank n, so A transpose A also has the rank n, and the size is n by n. So if this is A transpose A, the gram matrix is a full rank matrix, so it can be inverted. That is important, which is why we said this is solvable, because A transpose A can be inverted, and it is symmetric also. It's got other properties which we might, I think we'll talk about it in 2 weeks time. The smaller matrix is full rank, square, symmetric. We will later call this a positive definite matrix also. So let's look at the properties of the projection matrix once more. How do you get the projection to begin with? So we'll use the projection matrix. So we have the equation AX equal to B multiplied by A transpose so that it is solvable, and we have the hat here. So we get X hat, the solution is A transpose A inverse, it is invertible, it's a square invertible matrix, times AT times B. We also have AX hat is equal to B hat, because that is the definition. So this is what we started with, AX hat is equal to B hat. X hat, remember, was the collection, the set of scalar multiples that of the basis matrix A that will give you the projection in the case of the two-dimensional example that we did. So B hat is equal to AX hat. X hat we already have here. So we just have to multiply by A. Then we get an interesting thing here. B hat is equal to A transpose A inverse, A transpose B. You get something that is quite interesting. Looks complicated, but if you think about it, we had the projection matrix for vector A, just for a vector, projecting B onto it. We had the projection matrix A transpose divided by A transpose A. This was a projection matrix, and this we can write as, can split A, and this, remember, this guy in the denominator is just a number, it's the square of the norm, just a number. We can split the top part and then write that as A transpose A, that's just a number, inverse means as a reciprocal. That's what we have there, A transpose A inverse times A transpose. Just that here I have vector, there I have a matrix. Vector, of course, is a matrix of one column. Here you have multiple columns. Now, if you think about it, if you just look at why not expand it and write it this way, get just B hat is equal to B. So B hat is that is the projection matrix. So this you have to think about. this I'm going to leave to you as an exercise. If I have A transpose A x hat and A x hat is just B hat and A transpose B, then I have A transpose B hat is equal to A transpose B, then does that imply B hat is equal to B? Does this imply AB is equal to AC? Does it imply that B is equal to C? That is something that you have to think about and maybe do this in Sage Math with a couple of examples, construct examples to either prove or disprove this one. Now, what we said earlier about the projection matrix will still hold. If you project twice, whether onto a vector or onto a subspace, projecting twice is the same as projecting once, which means P square is equal to P. So if I take P square, so take P here and multiply by P once more, then you can see that it is actually just P because this guy and this guy will cancel because A transpose A is invertible and there is the inverse right there. So this whole thing here becomes just I, and I just disappears. So this thing is just as good as not being there. The rest is just P. P is what they call idempotent. The second one is more interesting. Projection matrix is symmetric also. The proof is the hint to the proof is here. If I consider A transpose B, this is going to be the same as A transpose B hat. If you take a vector A and B, I want to take the dot product theta here, and it's the same as taking the projection B hat, which will be B cos theta, and then multiplying by A, that will give me A dot B. And if I just take B hat, which will be just this, and that also is A dot B. So A dot B hat is the same as A dot B, just because of the triangle right there. So I can write this is equal to A transpose P B, because B hat after all is B hat, projection operator operating on B. Now if I project A onto itself, you're obviously going to get A. So if I take A and project it, this is going to be equal to A. If I take transpose on both sides, then I get A transpose P transpose is going to be equal to A transpose. So I can take that guy there, A transpose B is the same as for A transpose, I put this one in there. So I get A transpose P transpose B, and from the blue guy here, I get is equal to A transpose P B. This I say will say that P transpose is equal to P. So this is my proof. So take a look at this proof and see if this is actually true. Well, in any case, P transpose is equal to P will satisfy this condition. So that is the proof. P transpose is equal to P. The two conditions that we have, 1 and 2. So those are the two things that we will use to show that P is symmetric. And again, you can take P transpose, which will be the whole thing transposed, and because of the product rule, the first one will be A transpose transpose, which is A. The second one will be A transpose A, the whole thing inverse transpose, which is the same as the transpose inverse, and that is the same as this. And then the last element will be A transpose. So you just apply the product rule of transposes and the fact that transpose of an inverse is the inverse of the transpose, and then use the fact that A transpose A is actually symmetric, and then you will get that the whole thing is symmetric. Quite neat. So now we were working with a two-dimensional subspace in 3 dimensions, but we can actually generalize this. So this is actually the same as projecting to the column space of A, where A was a 3 by 2 matrix, a full column rank tall matrix, but it applies to any matrix that is full column rank with more rows than columns. So in order to make Ax equal to B solvable for a member of Rm by n, all you have to do is to multiply both sides by A transpose, which is what you have to remember. This is what you really have to remember. So again, you're not actually solving it, you're getting the best possible solution. And this is also called the least square minimization. Do you know where this square thing comes from? Can you think about, actually I hinted at it right in the beginning. Can you think of why this best possible solution is actually least square minimization? Yes, we're using Euclidean norm, and Euclidean norm actually inherently has squares in it. And we're trying to find the smallest error vector and smallest error vector in terms of its Euclidean norm. That's why it is a least square minimization. But we are not actually doing any kind of minimization a la calculus. We're actually doing it in a much more elegant linear algebra way. So let me just list the solutions here. So x hat is A transpose A inverse A transpose B. Again, don't try to memorize all these things, but just memorize that Ax equal to B. The moment you multiply both sides on the left by A transpose, you will get something that is solvable in terms of x hat. That's what you have to remember. That's easy to remember. And then from that you can derive all these things. Projection is going to be Ax hat, and that is, since x hat is right there, it's multiplied by A. And the projection matrix is whatever is multiplying B to give you B hat, and that is there. Why not expand it? Then do the associativity property and then write P is equal to I. Why not basically apply product rule of inverses to A transpose A inverse? A B inverse is equal to B inverse A inverse, provided that these two guys do exist. If they are invertible, if they are square and invertible matrices, then this equation actually does work. But in this case, they are not square, so they are not invertible. A and A transpose, I mean. So we cannot actually do the expansion. If A happen to be square, what would that mean? And invertible. It would actually mean Ax equal to B is solvable, and A column space is all of Rn. Projection of an n-dimensional vector to Rn is actually the vector itself, and P is actually just the identity matrix, because you're projecting a vector into its coordinate space and you get the vector back. So like I said, it is impossible to find any kind of mathematical inconsistency within linear algebra. It is actually beautifully sewn together. Everything fits together very nicely. So you cannot expand it because A is not a square matrix, so it's not invertible. If A were a square and full rank matrix, then the projection is the same as the vector that you're projecting, because column space is all of Rn, and the projection is actually the same as the identity matrix. Now, there is one little thing that I want to highlight, because you might come across this. There are what people call hat matrices. Projection matrix is called the hat matrix because P is the one that takes a vector and gives you its hatted version. So because of that, people call it, especially statisticians, call P a hat matrix. So what it does is it takes a vector and gives you a vector in the column space, the projection matrix. And there is another hat matrix typically called P2 that takes a B and gives you a vector in the left null space, and that is called P2. It's the other hat matrix. It's basically just I minus P. So there is a box in the textbook actually explaining this to you. It's not that critical for our application in computer science, but just in case you read up something online or something, you might hear about hat matrices and you might think that I did not teach you this one. If B is actually already in the column space, then the projection to the column space has to be B itself. And if B is orthogonal to the column space, then the projection is 0. All those things you should verify. So let's move on to the application of the projection. So given some data points, say coordinates for instance, how to get the best possible line through them. So I have 4 data points like 1, 1, 2, 2, 3, 2, 4, 5. Those are the coordinates, x and y coordinates. And if I plot them in Excel actually and find a trend line, I actually get a trend line, and it will actually show me the equation to the trend line y is equal to 1.2 x minus 0.5, and the r square, the coefficient of determination, is 0.8. All these things actually come from linear algebra, come from whatever we did so far. So that's what we want to kind of understand. Now, clearly these points are not consistent as a system of linear equations. So that's what I want to show you first. If I were to take just the first 2 points, 1 and 2, so I would get that line. If I were to take points 2 and 3, I would get that line. If I were to take 3 and 4, I would get that line. None of those 3 lines is actually a good fit. So throwing away anything other than 2 points is always a bad idea, because there is information, and you can see that the best possible line is actually the blue dotted line, blue dashed line rather, and all the red dotted lines are bad lines. So we have to get to the dashed line. So how would we do this? So I have data points, and what I'm saying is that there is a model mx plus c is equal to y. So I just put in different values for x and y in mx plus c equal to y. So I get 1, 2, 3, 4 equations. If I have that, I have 4 equations and 2 unknowns, m and c, 2 unknowns. So let's find out if there are solutions. So I want to write it in the form of Ax equal to b. So A, my matrix, is 1, 2, 3, 4. That is the coefficient of the first unknown, m. So 1, 2, 3, 4. And the second unknown is c, 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 c. So the coefficient is 1. So 1, 2, 3, 4 and 1, 1, 1, 1. That is my matrix A for this system of linear equations. 4 equations, 2 unknowns, M and C. And now my unknowns are M and C and my constants vector is 1, 2, 2, 5. Now I'm writing Ax equal to B and there is no solution for this one because the equations are not consistent. If you actually do the Gauss-Jordan elimination, you will see that the third row will have something that implies 0 equal to non-zero. Now I can go and do my recipe. I'll take A transpose A and A transpose A inverse. So I'll do all that. A transpose A inverse A transpose. So a lot of arithmetic calculations to be done. After doing all that, your reward is that you get X hat, which is the best possible estimation of M and C, M hat and C hat. That will be equal to X A transpose A inverse A transpose B, and I get this. And if you look at it, it is 6 by 5, that is 1.2, and minus half, which is minus 0.5, which is what you had, which is what Excel told you. So that's what you will get. So what Excel is implementing is not an iterative way of getting at the solution. It's actually a closed form computation. Given some data points as coordinates, how to get the best possible line through them. What you will do is get M hat and C hat, the variables in the system of linear equations M and C, those are the variables, and you have to find the best values for those, and that will give you an equation, and that equation is the best possible line. And even the coefficient of determination is given by the error vector, the green E vector, because that shows you how far away you are, actually the difference between the projection and the original constants vector, but that gives you an indication of how good your fit is. That was the first example. The second example, I want to go back to, I think this was week 5 or 6 or something, where we had 3 equations that did not have a solution because they went through 3 different points. There was no common point in the coordinate space. X plus y equal to 5, x minus y equal to 1, and 3x minus y is equal to 9. 3 different lines, no common points. And at that point I asked you what the best possible solution would be. We kind of guessed that it could be the centroid maybe, but now we are much more sophisticated in terms of our linear algebra ability. So we can actually write Ax equal to B, 1, 1, 1 minus 1, 3 minus 1, that is A. My x vector is x and y, and B is 5, 1, 9. And then I can take A transpose A transpose A transpose A inverse, and then that. Then I can get the best possible value of x and y. I get 3.5 and 1.83. That is the best possible value, and that is actually inside this triangle. 3.5, that is here, and 1.83 is actually somewhere here. That doesn't look like the centroid, but it is somewhere inside the triangle. And if you just compute the centroid, which is just the mean of all the x values and mean of all the y values, that gives you 2.17. That looks more like here. So there is a difference between actually doing it the linear algebra way and then our intuition. Look at the centroid. The reason why the centroid doesn't look like the right one is because we are not actually working in this space. We are working in a different space. We are working in the vector space. And there is one more reason. That reason is something I would like you to discover on your own. And if you cannot discover in 1 or 2 weeks, maybe ask me in the last lesson, and then I'll tell you what it is or what I think it is. I will invite you to figure out why the best possible solution is not the intuitive centroid, but something else. And this has some implications on the k-means algorithm, which actually uses the centroid, and how it compares with linear regression, etc. So it's got implications in machine learning. So that's why I would like you to think about it. Let's take a real data set to understand this better. So the whole data set is basically a matrix. So I have a data set here. This is a real data set that I collected from my students a couple of years ago to do some project. So I asked them for their height, their weight, and their length of hair estimated, and their age, and their sex, male or female. So as you know, males tend to be a little older than females in Singapore because of the national service, and they tend to be a little taller and heavier, and they tend to have shorter hair. And we can probably create a statistical model out of it, which will be a linear regression model. So each column is a column of a feature. height or weight or length of hair or something. It's called a feature. And each row is an observation. So there are 5 features here and many observations, 127 really. So it is a very tall matrix. You have to be a bit careful because in some situation, people think of features as rows and observations as columns, though not very common. And so you have to be careful about which way it is really. So let's look at the data. So I have 127 numbers. If I were to plot them, I have 5 different variables really. I think I'm going to ignore age. I'm showing height along the x-axis, weight along the y-axis. So people who are taller, they tend to be heavier. So there is some kind of line here. And then I'm showing the length of hair by the size of the point. So you can imagine that there is an axis coming towards you from the plane, and that is small numbers farther from you and bigger numbers closer to you. So bigger numbers look bigger because they're closer to you. So bigger bubbles for people with longer hair. So you can kind of see that these blue points are probably girls. They tend to be smaller and lighter, and the orange points are probably guys. So this is a visualization, and we're trying to build a model for this. So it's not just one variable versus one variable, but we have more than that. So let me look at it once more. What I want to do is to take height and length of hair as independent variables, things that I can measure. I want to take weight as the output variable, something that I want to predict. So I have some data here. I have the red ones that are inputs and the green ones that are output. So that is my training data. And I'm going to I want to implement an intercept that I'm going to add 1. Remember, for mx plus c, for c we had ones everywhere. That column of ones will happen here also. So I'll have an intercept implemented by 1. So I'll start with ax equal to b. My A matrix will be all my red numbers here. B will be my independent numbers. And X is my parameterization. X really is my model. So A is that. Regression parameters, typically people use the symbol beta for it. So it's a vector, beta vector. That is a model. So the 3 numbers there will specify the model for you. And my B vector is the output. That is the what we call the dependent variable y, the thing that depends on the input. So this is what we have. And to use the right nomenclature and right symbols in the world of linear regression, people usually write ax equal to b as x beta equal to y, and the solution then will be x beta equal to y will not have a solution, but multiply by x transpose on both sides, you will have a solution that will give you the best possible estimation of the parameters beta. So that's the game that we're going to play. So x is called the design matrix, beta is the model, the statistical model. Those are called the regression parameters. There will be n of them plus 1 because I added the intercept. And in most programs, most statistical programs, you will have the freedom of saying that the intercept is 0. So there's a no intercept model also, in which case the regression parameters will have only n parameters coming out of the model of the program. Then the target variable will be the training data set. You will have as many as the number of observations. Now, in order to get the statistical model, the regression model, all you have to do is to just do this multiplication. You have x, so take the x transpose. You have x transpose x, the gram matrix, as a small matrix, takes its inverse, multiply, and y is all known in the training data, and that gives you a set of regression parameters coming out of the data. That is the training process. As you can see, it's not iterative, it's straightforward matrix multiplication. We have very good algorithms to do this, and it is determined. It is a very beautiful algorithm to actually get to the regression parameters. Okay, so that's what I wanted to show you. So x beta equal to y, x is the design matrix, and that is the measured independent variables. Beta is the model regression parameters. Y is the measured dependent variables in the training data set, and based on the training data set, what's the best possible beta that gives you, and that is given by x beta is equal to y, multiply both sides by x transpose and put a hat on beta, and that's it. That is the best possible beta that you can get. So now you might ask, why are we doing this? Why do you want to get this model? What's the purpose of getting the parameters beta? Because once you have the model, you can predict a new weight. If a new person comes in, I don't have a weighing scale, but I only have ways of measuring the height and the length of hair. Once I have the model, I can actually predict what the weight is going to be. And this is basically the basis of predictive analytics using linear regression. It's a supervised machine learning algorithm because we have labeled training data. So the way of doing it in linear algebra is elegant, geometric, thinking about the projection. Calculus will give the same answer, of course, but it's tedious and messy. So the squares, actually the fact that it's the least square minimization, the square actually comes from the fact that is we are using Euclidean norm. Alright, let's summarize what we learned today. So projection to subspaces. We started with projection using the angle, the cosine of the angle. That is what we did earlier. And then we projected using the orthogonality, the linear algebra way. And then we looked at projection as an operator or as a transformation and derived the projection matrix and looked at the properties of the projection matrix. Is idempotent, which means P square is equal to P. It is symmetric, which means P transpose is equal to P. And we proved those things. And we said that in general, Ax equal to B may not have solutions if you have too many equations. But in order to get the best possible solution, all you have to do is to multiply Ax equal to B on both sides on the left by A transpose. And that gives you the best possible solution, X hat. And then B hat would be the projection of B onto the column space of A. That is Ax hat. And Ax hat, as you can see, is a member of the column space of A. And the error involved will be a member of the left null space. Then we went on to develop the linear regression algorithm using the projection idea. And by renaming A and X and B, like the design matrix, the parameters beta and the dependent variable. And then we use the same idea of multiplying by A transpose, X transpose in this case, to get to the best possible estimation of the linear regression parameters. So from the training data, you get the design matrix. You also get the dependent variable in the training data. Those are the labels. And you obtain the parameter estimate beta from our linear regression equation. And now you get testing data, a new data point that is coming in where it is not labeled. And you can estimate what the label should be. And that is a predictive analytics model, supervised learning. And once you have beta, all you have to do is to say that the new y is going to be equal to beta transpose times the new x that is coming in. So new y corresponding to a new observation is just given by multiplying by just writing one linear equation based on the statistical model. That is linear regression. That is all there is to it.